Welcome to this explainer. Let's just jump right into it, because today we are looking at something truly magnificent. We're going to examine the grandest, most incredibly powerful forces operating right on the surface of our planet. I'm talking about Earth's master sculptors. We have the relentless, grinding power of ice and the constant crashing energy of ocean waves. These two forces are out there, literally right now as we speak, fundamentally shaping the world as we know it. Have you ever just stopped to look at a jagged mountaintop or maybe walked along a beautiful coastline and ask yourself, how are towering peaks like Mount Everest or your favorite sandy beaches actually made? Because, they weren't just dropped there. They're actually the temporary results of an incredibly active continuous process of geological transformation. The Earth is constantly carving away at its own surface, destroying old features and building up brand new ones in this never-ending cycle. Okay, let's dive into our roadmap for today. First, we'll meet our two master sculptors. Then we'll head up into the mountains to observe glaciers, the heavy grinders, and the debris they drop off. After that, we'll travel to the coast to watch relentless waves build shorelines. And finally, we'll discover why these coastal structures are actually nature's most essential defense system.
Section 1. The Earth's Master Sculptors.
To really get this, we need to understand our two main artists. Ice and ocean waves are totally distinct forces, and they use entirely different tools. One uses crushing, slow-moving weight, while the other relies on rapid, unyielding pounding. Basically, glaciers use friction and sheer weight, while waves use constant lashing to sculpt the Earth. Think about the incredible contrast here. A glacier might move mere inches a day, right? But the sheer, unfathomable mass of thousands of feet of solid ice generates tremendous friction that can grind down solid rock. On the flip side, a wave might not weigh much compared to a glacier, but it strikes the coast every few seconds, day after day, year after year. That constant, rapid churning eventually just shatters cliff sides. Section 2. Glaciers, the heavy grinders. Way up in the freezing peaks, ice accumulates over centuries and slowly moves down the mountain, literally cutting into the rock beneath it. The most common landform you'll find left behind in these glaciated mountains is called a cirque. Now, cirques are deep, long, wide basins with vertically dropping high walls at their heads and sides, cut entirely by moving ice. Imagine a giant ice cream scoop taking a massive bite out of the side of a mountain. That concave basin is your cirque, and you'll usually find them right at the very head of a glacial valley. But the sculpting doesn't stop with just a single basin. As these cirques are rowed further and further backward into the mountain, which is a fascinating process called headward erosion, the divides between them get narrower and narrower. Eventually, they turn into jagged, sawtoothed ridges known as arêtes. And if three or more of these radiating glaciers cut backward until their cirques completely meet in the middle, they form a horn. This is a high, incredibly sharp-pointed and steep-sided peak that just towers over the landscape. Now, what's really interesting about this is that the Matterhorn in the Alps and Mount Everest in the Himalayas are actually just glacial horns. Yeah, no way, right? The most famous, iconic, imposing mountain peaks in the world weren't simply pushed up into those sharp points by tectonic plates alone. Their specific, jagged, sawtoothed shapes are actually the result of ice slowly carving away the rock on all sides over millennia until literally only that high, sharp point remained. Section 3. Glacial drop-offs, depositing debris. So the ice carves the mountain away, but all that rock doesn't just evaporate. When the glaciers eventually melt, that debris has to go somewhere. What the ice leaves behind generally falls into two distinct categories: glacial till versus outwash deposits. Glacial till is the unassorted, coarse, and fine debris dropped directly by the melting ice. Because it's just dropped right there in place, the rock fragments remain jagged and angular. On the flip side, we have outwash deposits. When the ice melts, it creates streams that wash smaller rock debris down the valley. And because this material is carried and rolled by running water, these deposits are roughly stratified, they're assorted by size, and their edges are all smoothed and rounded out. That glacial till we just talked about, it forms massive ridges of debris known as moraines. And there are several types, depending on exactly where the glacier decides to leave them. Terminal moraines are long ridges of debris dumped right at the end or the toe of the glacier. Lateral moraines form along the parallel sides of the glacial valley. When glaciers merge together, their lateral moraines can combine right in the center to form what we call a medial moraine. And finally,
As a glacier rapidly retreats, it can leave this uneven or regular sheet of till across the entire valley floor, which we call a ground moraine.
Section 4. Coasts, the relentless waves.
Okay, let's shift our focus away from the quiet, freezing mountains and travel down to the loud, relentless ocean coasts. This is the absolute domain of our second master sculptor, the wave. Now, coastal sculpting depends entirely on the type of canvas the ocean is working with. High, rocky coasts, like the west coast of India, feature hillsides that drop sharply into the water. Here, the power of the ocean is really focused on destruction. Erosional forms dominate as waves pound the solid stone. By contrast, low sedimentary coasts, like the east coast of India, slope very gently into the water. Here, depositional features dominate. The ocean uses its energy to churn and arrange sediments into brand new coastal features. Let's look at how erosion actively tears down a high rocky coast. It is an incredibly dramatic sequence. Step 1. The relentless lashing of waves against the base of a cliff smashes rock debris into the wall, creating deep hollows. Step 2. Over time, these hollows are deepened and widened by the pounding water to form deep-sea caves. Step 3. Eventually, the rock roofs of these caves simply cannot support themselves and they completely collapse, causing the entire sea cliff to recede further inland. Step 4. This retreat often leaves behind temporary, isolated pillars of resistant rock standing all alone out in the water. We call these sea stacks. But ultimately, even these towering sea stacks will be battered away into nothing.
Section 5. Coastline builders, sand and sediment.
Because just like we learned with glaciers, destroyed rock doesn't just vanish. The sea takes that eroded sand and sediment and literally constructs temporary shifting landscapes. This brings us to beaches, which are the most characteristic feature of depositional coastlines. You might be super familiar with sand, but consider the shingle beach. A shingle beach is a coastal patch containing excessively small pebbles and cobbles that have been rolled and rounded by the water. And this brilliantly illustrates a larger system at work. Because just behind these beaches, the wind lifts and winnows the lighter sands directly off the beach surface, carrying them inland just slightly to deposit them as massive rolling sand dunes. Everything is perfectly connected in this cycle. On those gently sloping low coasts, the waves churn bottom sediments to create a truly amazing sequence of features. First, a ridge of sand called an offshore bar forms parallel to the coast, completely underwater. Second, as more sand is continuously added to it, it breaches the surface and becomes an exposed barrier bar. Third, if this bar connects to the headland of a bay, it becomes what is known as a spit. Fourth, as the spit grows, it can entirely block the mouth of the bay, forming a calm, enclosed lagoon. And finally, over a really long period of time, that lagoon fills completely with sediment from the land and the wind, evolving into a wide, solid coastal plain. The ocean is literally building new land right before our eyes. Section 6. Nature's Essential Defense System. Up to this point, we've kind of looked at these geographic features as beautiful, fascinating sculptures. But this geography isn't just nice scenery. It is absolutely vital for human survival. A quote from our source material lays out the stakes perfectly. Quote, "If we do anything which disturbs the sediment budget, these coastal forms will get eroded away, leaving human habitations to bear first strike of storm and tsunami waves." So the crucial point here is that those offshore bars, those barrier bars, beaches, and dunes, they're not just piles of sand for us to vacation on. They are our very first buffer. They absorb the sheer destructive force of incoming storms and tsunamis. The sediment budget is that delicate balance of sand being deposited versus eroded. If we go in and block rivers or mine too much sand, we literally starve the coast of the materials it desperately needs to build these defenses. Which leaves us with a pretty high-stakes reality to consider. If we continue to disrupt the natural sediment budget, are we systematically dismantling our only buffer against the next major tsunami? Earth's master sculptors, the ice and the waves, have spent millennia carving and building the very coastlines that protect us. It is really up to us to understand these immense forces, respect the delicate balance they create, and ensure that our actions don't wash away the natural defenses we rely on. Thank you so much for joining me on this explainer. Keep asking questions, and I'll catch you next time.